Hello there. Let's do some switch basics. Because switches are so widely used nowadays, you find them in pretty much every LAN you'll come across. But before we can appreciate why switches are so special, we need to talk about some of the things that came before them. So let's do some pre-switch technologies. And the main LAN device that predates switches in a way that you would recognize a LAN as a LAN would be hubs. Now, the symbol for a hub is usually a square with one arrow in one direction, although I have seen some icons and templates that use two arrows, but they'll always be pointing in the same direction. Now, a hub is what we call a multi-port repeater. It has multiple interfaces and is designed to repeat the signals it receives. So it basically works at OSI layer 1. It's a purely physical device. And its method of operation can be remembered in one single sentence. It receives a signal, it amplifies that signal, and then it sends that signal or repeats it out of all of its interfaces. So if I were to connect a couple computers to this hub, and let's say the one on the left is the source of the traffic and the one in the middle is the destination. The traffic would make its way from the source computer to the hub and then out that interface to the destination, but it repeats it out of all interfaces. So it's going to go to that third computer who's just sitting there minding its own business, and now it's receiving traffic that is going to have to process and work out, oh, that's not meant for me. Now that doesn't sound too bad in a small network like this, but let's scale that up. Let's say we've got multiple hubs and multiple computers connected together, and let's say the source and the destination are both on the left hub there. The source computer sends its traffic, and obviously it goes out the other interface to the destination, but remember, it's going to go out of all interfaces. So it's going to go to that hub on the right there. And now that hub is going to do what the first one did. Take that signal, amplify it, and send it or repeat it out of all interfaces. So those two computers over there get stuff that they're not meant to get. They're going to have to process this until they work out this is not meant for them. So to try and introduce some usefulness and intelligence into our network, we introduced bridges. Now, the icon for a bridge is this thing. Sort of looks like a suspension bridge without the two parts on the side going down to the ground on each side of the canyon. I have a very visual mind, I'm sorry. And it was our very first major layer 2 device for LANs. Now, being layer 2, it is able to work with MAC addresses, and it will learn the MAC addresses from the frames that it is processing. And as it learns those MAC addresses, it associates them with the interface that it received the frame on. So that means that when a computer is connected to a bridge in any way, when traffic it sends reaches that bridge is going to pay attention to the source MAC address of the frame or the layer 2 traffic. And that bridge will now remember that MAC address of 0102.03.04.05 and associates it with that interface. So if we take that network we were looking at just now and take that cable out from between those two hubs and stick the bridge in the middle, what we're going to land up with is a network where a little bit of intelligence will be present. So now obviously we're going to care about these guys having MAC addresses. As you can see, I've made some easy to read MAC addresses: 0102.03.04.05 AA, BB, CC, DD. Literally it's the last two digits that differ. Please be aware that when you're tackling the Network Plus exam, they might not be as nice with what the MAC addresses look like, so just read them carefully. But for learning purposes, I think we can get away with making the stuff a little bit easier to read and to talk about. Now, as before, we have the same two PCs acting as source and destination. Now, the bridge is going to learn the MAC addresses. We've skipped ahead, and the bridge now magically knows it already. What will actually happen, though, is when the bridge sees new traffic arrive, it will look at the source MAC address field of the frame, and if it's new to this bridge, it will associate it with that interface. So it now knows that MAC address blah 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 AA and BB is on the left interface, and MAC address blah 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 CC and DD are on the right side. Now, we can have the source computer sending some traffic out. The hub that traffic arrives on still does what a hub does, out of all interfaces. But this time, we're actually going to be keeping track of source and destination MAC address. So out it goes, but this time, it gets to the destination, fantastic. The recipient receives it, sees their MAC address in the destination MAC field, and carries on processing it. But the hub still sends that one frame out the interface it actually didn't need to. But the hub doesn't know any better, so we can't blame it. The bridge will have a look at the source and destination MAC address and go, I see that the MAC address for the source and the destination is on the same interface. There's no need for me to send it out the other side, so the bridge does what's called a filtering decision and chooses not to forward that traffic. So in this situation, it's nice. The bridge has not sent the traffic to the other side unnecessarily. However, what if the destination is on the other side of the bridge? Well, in that case, what's going to happen now, that traffic hits the hub, source MAC is AA, destination MAC is CC, and the hub doesn't care because it's layer 1, out of all interfaces. The bridge looks at the source and destination MAC address and realizes, yes, the source MAC is on the incoming interface, but the destination MAC address is on the other side. I better send it out the other side. So now it arrives on another hub. Now that it's on another hub, that hub is going to do what it does best, out of all interfaces. So it does get to the destination, but it still went to everybody it didn't need to go to. Thankfully though, when we do look at how switches work, they do this just better. But there's another interesting technology that you need to know about. CompTIA is definitely going to want you to know about something called CSMA-CD. And the reason is we still use it in our LANs, even though we've got switches now. You'll see why I said that the way I said it. So first of all, what's this acronym for? Carrier sense, multiple access, with collision detection. That's what the slash is for. So this is a Ethernet service designed back in the era of hubs and even before hubs when we used to use something called a bus topology. So this is what a bus topology would look like. A bunch of computers all connected to the same cable. This was actually very common when we used to use coaxial cables for our networking. Now, why is this necessary? Well, in a network where everybody shares the same single cable, we have some potential dangers. So CSMA-CD outlines normal communications and its normal conditions and rules for all of these computers here is listen before you send traffic onto the network. When you listen to the network, one of two things will happen. Either the network is quiet, no one's using it, you can send traffic. Or you listen to the network and you hear it's busy right now, you hear someone's using it. You wait till it gets quiet, then you can have your turn. Now that sounds great, but there's a problem with it. What if two computers listen to the network at the same time and come to the conclusion at the same time that it's quiet and they both send at the same time? This traffic starts making its way down the cable, the electrical signals start going to the computers connected, but at some point these two signals are going to run into each other, and we have now what we call a traffic collision. Now, nothing dangerous is going to happen, so don't worry, but the electrical signals that make up the traffic are going to start running into each other and messing with each other, over-amplifying or negating each other. Going to be unpleasant. Now, what is CSMA-CD going to do for us? Well, it says carrier sense multiple access with collision detection. So we're going to detect the collision and recover from it. So when the collision occurs, the first PC that sees or technically hears the collision will send out something called a jam signal. So let's say, for instance, that computer was computer B with a little blue dot above it right now. It sends out a jam signal throughout the network and everyone sees that jam signal. Now, what makes the jam signal special is it lasts for 3 times the duration that a normal network transmission would last. So this jam signal will definitely outlive the collision. So the collision obviously dissipates because the signals eventually stop being sent, but the jam signal carries on going. So we know that all the other computers in the network have heard this jam signal. Now, all the PCs will have to set for themselves a random timer. So they're all going to have a little clock, and they're all going to set for themselves some random times. They probably will not be nice multiples of 10. I just did this for the ease of reading and speaking. But in reality, it'll all be random numbers. Some will say 10 milliseconds, some will say 13, some will be 2. It'll be random, it'll be all over the show. When the jam signal ends, the random timers begin counting down to 0. So the jam signal now goes away, and these timers can start working their way down. But what happens when they reach 0? Well, you cannot send any traffic until your timer reaches 0. However, you can still receive it. Obviously, when your timer reaches 0, you can have your turn. So judging by it, we've got PC A with 10 milliseconds, B with 20, C with 40, and D with 70. So 10 milliseconds will pass, and A gets down to 0 milliseconds, and A can now transmit that traffic. Now remember, all the other devices are still counting down, but they can still receive while they're counting down. They just can't send anything, so they can't reply. But that's fine. A got its traffic out. Lovely stuff. Now the timer is carry on running down, and another 10 milliseconds pass, and B hits 0. But B's got nothing to say, so it makes no difference to B. Another few milliseconds pass, and C hits 0 as well. C didn't have anything to say, so it makes no difference. Then another 30 milliseconds pass, and D hits 0 and can send its traffic out. And now we have successfully recovered from that collision, and the two devices that caused it were able to retransmit that data. And that's fantastic. And this used to work very well years and years ago when our LANs were pretty simple and small. But obviously, you and I both know our LANs are no longer simple and they're no longer small. So we needed something better. Don't worry, you'll see why. So first of all, collision domains. We want to be able to recognize and identify collision domains in our network. Any area in your network where a collision could occur and you need CSMA-CD to bail you out is a collision domain. Now hubs create one big massive collision domain, and switches create many small collision domains, generally one per physical interface. So if we plot a little network out here, where we're going to have a router just to break everything up, and on the left side we're going to have a hub and 2 PCs. And on the right side, we're going to have a switch and 2 PCs. Jumping the gun a bit, but that's the switch. Now, this is where the collision domains will be. Hubs create one massive collision domain. Switches create one per interface. And the thing about the switches one is it's actually beneficial to us. The reason being, in the hubs collision domain here, if a collision occurs on this cable over here, this computer and that interface of the router have to take part in CSMA/CD, despite the fact that they were nowhere near the collision. So they have to suffer even though it was a collision on another interface. Whereas over here, with the switch, if a collision occurred there, between the switch and the PC, that PC and that switch's interface over there have to do CSMA/CD. This interface and connection to the router can carry on as per normal. This interface and that computer can carry on as per normal. This is one of the benefits of a switch. Having many smaller collision domains makes sense. If this was, for example, different cities or villages, towns, whatever, having an accident in one town affects other towns. That doesn't make sense. If there's a traffic accident. If there's a traffic accident in that town, why should people in the neighboring towns suffer? Doesn't make sense to me. So this is a better option. This is nicer. Now, before we get into the switches properly, we want to look at MAC addresses as well. We have looked at MAC addresses a couple times already, but let's just make sure we're all clear on exactly what MAC addresses are. And they are a form of physical addressing. MAC addresses, or Media Access Control addresses, are a popular OSI Layer 2 addressing mechanism. They are made up of 48 binary bits. And thankfully, we don't have to memorize those 48 ones and zeros because we'd rather write them using 12 hexadecimal characters. And they are built into your network card. They are literally etched into the chips of the network card controller circuit. So they are part of the network card. The only way you're going to get a real new one is by getting a new network card. Now, you might have come across this thing called MAC address spoofing. And if you're working with Windows 10 or 11, you might have seen that when you connect your computer to a guest wireless, Windows offers you the ability to randomize your MAC address for security. That is called MAC address spoofing, and it is a way to tell your computer to lie about its MAC address. Just before the traffic leaves the network card, a piece of software running on the computer intercepts that and removes the real source MAC address from the frame and puts a fake one in there, tricking the network into thinking, oh, that's actually what your MAC address is. Now, it doesn't actually change what your MAC address is. It just changes what the rest of the network thinks it is. It's sort of like if somebody gives you a fake phone number instead of their real phone number. You won't know it's fake until you try and call them. Guys, if you don't know what this is about, ask the ladies, they'll tell you. Sorry, ladies, I just let slip that secret. My bad. Anyway. Now, the interesting thing about MAC addresses is they're pretty guaranteed to be unique. But the problem is, even though they're unique, they are not predictable, which is why we only really use them for LAN communications and not internet communications. IP addresses are not unique, as you've seen with what we've done previously with the IPv4 videos, the NATing, all that good stuff. But with IPv4 addresses, they are predictable. As long as I know what your address is, I'm pretty certain of how I can use that to get traffic to you. Whereas a MAC address, I've got to find out what it is at some point. So let's understand, why are they guaranteed to be unique? Well, the MAC address is broken into two parts. The first half, the first 24 bits or 6 hexadecimal characters, are called the OUI, or Organizational Unique Identifier. And the manufacturer of a network card, or any network appliance for that matter that needs a MAC address, has to approach the IANA and a couple of other numbering and naming authorities to get that OUI. So if you go and buy a bunch of network cards from a particular manufacturer, the chance of them having the same OUI is pretty damn high, especially if they're rolled off the same production line at the same time. Now, the reason why I say it's pretty damn high is because a lot of network card and network device manufacturers have several OUIs assigned to them. But they have to use that particular string of 24 bits or 6 hex characters. And the second half goes by a couple different names. I've seen vendor assigned, I've seen interface ID, I personally hate that one. And then the most standard name I've seen is the network interface controller specific portion, which is unique to the network card. And one of the agreements that the manufacturer of the network appliance has to abide by is that they will make sure that they give every network card they produce a unique NIC portion for the given OUI that they were allocated. So if we stick an example MAC address here, 0017C84F30F2. The first half is the OUI, and the second half, the 4F30F2, would be unique to that network card. No other device should have that exact combination of OUI and interface ID. Somebody else could be running around with an OUI of 0017C9 and still use 4F30F2, but it'll be unique still by one digit. But there is a MAC address I know you will have in your network at some point, and that MAC address is called the broadcast MAC address. It is all binary ones, so it's 48 ones. I'm not typing those all out, sorry, I'm a bit lazy. We can write it with 12 hexadecimal Fs. It's the same thing. And this is a MAC address that we use as a destination MAC address when we want to make sure the traffic goes everywhere. Switchers will see this MAC address and go, okay, I'm going to send this out of every single interface except the one it arrived on. So when I want to make sure traffic goes to everybody, I use this destination MAC address. So now let's get into the switches properly. So first of all, let's look at what we already have. Hubs and bridges. Hubs have loads of interfaces, but they've got absolutely no forwarding intelligence. Then you've got the bridges. They've got forwarding intelligence at layer 2, but they don't have that many interfaces. That's the big downside of bridges. So a bunch of network engineers got clever. They booked a hotel room and put the hub and the switch in that hotel room. And they waited a long while. And then after a long while, out came a switch. So the switch gives us loads of interfaces, and every one of those interfaces has layer 2 forwarding intelligence like a bridge does. Now the way the switch will keep track of things is it's going to keep track of stuff with a MAC address table. And it's going to associate MAC addresses it learns by looking at source MAC address fields of traffic, just like the bridge did, with the interface that it heard the traffic on. And please be aware that the bridge can associate more than one MAC address with an interface. Looking at the switch over here, it would have learned that PC's MAC address on that interface, and at some point, these two PCs would have sent something to that PC. So that PC's traffic would have arrived there. The switch would have learned it in that interface. That PC would have sent something. It arrived there. The switch would have learned its source MAC address on the same interface. So switches can associate multiple MAC addresses with one interface. Please remember that. It's just like the bridge. The bridge remembered multiple MAC addresses per interface. Why shouldn't the switch? Now, there's a bit more to switch logic that I want to teach you about, such as switches will inspect the source MAC address of traffic arriving all the time. And what it does is, if the MAC address is new, it adds it to the MAC address table associated to that interface. If the MAC address is not new, it moves on to a forwarding decision. So the switches are always looking to learn, whether it's been running for 5 minutes, 5 hours, or 5 years. It will always want to check and see if it learns anything new. Then the switch will check the destination MAC address of the frame that arrived. If the destination MAC address is present in the MAC address table, the switch will only forward out of the interface that is associated with that MAC address. If the destination MAC address is not present, the switch does what's called a flood operation. It'll send it out of every interface except the one it came in on. This is usually done in the early stages of a switch starting up, when the MAC address table is still empty. The MAC address table resides in the switch's RAM and is never saved to permanent non-volatile storage. So power cycles, power trips, physical resets will clear the MAC address table. So when the switch doesn't know, it sends it out everywhere, in the hope that it gets the traffic to the intended destination, and the destination generally would reply. A lot of the upper layer protocols that we're going to get into in a later video, but I did allude to them in the TCP/IP video, are going to have some sort of response from the recipient. So the switch is banking on that to see that MAC address coming back at some point, so it learns it and can use it in the future, and then do the more precise forwarding operation. Then the other situation is if the destination MAC address is the layer 2 broadcast address of 12 hexadecimal Fs. It floods it out of all interfaces except the one it came in on straight away. It's not intending to learn with a broadcast. The reason being, the switch can tell when that's the destination MAC address, the sender of that traffic wants it to get everywhere. So let's have an example. Got a nice little simple network here with a switch in the middle. It's got interfaces 01, 02, 03. We've got PCA, PCB, and PCC. A has got the IP address of 192.168.0.1, MAC address 01.02.03.04.05 AA. B's got the IP address of 192.168.0.2, MAC address of B, and C has the IP address of 192.168.0.3, and the MAC address of blah 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 CC. And on PCA, the user types in to their command line ping 192.168.0.2. Now ping is just a simple layer 3 hello message. It sends a layer 3 message to the destination IP address and expects to get a simple hello back. Just checks basic connectivity. So PCA starts constructing this ping packet. It will populate the 4 key addresses, destination MAC, source IP, destination IP, with what it believes to be the best information. And obviously it starts out with source information, because obviously source information belongs to PCA. Source MAC address is 01.02.03.04.05 AA. Source IP is 192.168.0.1. Destination IP, we get it from the ping command, 192.168.0.2. Destination MAC address. If PCA hasn't spoken to the destination, it's going to have a bit of a problem, because what it does is it checks something that's got called the ARP table. The ARP table is the Address Resolution Protocol table, and it keeps track of known IP addresses and MAC address associations. So in other words, what MAC address is this person using? And like I said, if A has not spoken to B before, this table is empty. It doesn't know anything. So this ping packet is not going to work for now. Oh dear, dear, dear. So we're going to get rid of it for now, and we're going to introduce something that will allow A to find B's MAC address without knowing it at all. We're going to generate what's called an ARP request. Very similar fields. Source MAC 01.02.03.04.05 AA, PCAs. Source IP 192.168.0.1, A's. 192.168.0.2, the person we're looking for, courtesy of the ping command. But this time we put the broadcast MAC address as the destination MAC address. And the ARP request is basically a message saying, hey, whoever's got this IP address, please reply to me. I want to know what your MAC address is. So this broadcast now leaves the PC and arrives on the switch on interface 01. Now the switch has got an opportunity to start populating its MAC address table. So in this MAC address table, it's keeping track of its interfaces 01, 02, 03, and it goes, ooh, I've just received something new. And let's check source MAC address 01, 02, 03, 04, 05, AA. Nope, don't know that one. So let me put it over here so that I now have it for future reference. Now let me check the destination MAC address. Oh, it's the layer 2 broadcast. Oh well, no point me checking the MAC address table, says the switch. Let me send that out of all of my interfaces so that it gets to everybody. Now that it goes out to everybody, let's just get C out of the way. C will check this and realize it's not meant for it. C will see, okay, the person that they're looking for is 192.168.02. I am 192.168.03. It's not me, so it ignores this. But PCB will see it. PCB will say, okay, somebody with this MAC address and IP address is looking for this IP address. Ooh, that's my IP address. And it's an ARP request. They want to know what my MAC address is. So B says, all right, I better reply to this person. Now, B, being clever, will take this opportunity to populate its ARP table so that it knows, okay, that IP address is associated with that MAC address. And then it starts crafting an ARP response. B will put in its ARP response, its MAC address for the source MAC, its IP address for the source IP. Remember, this is a response from B to A. A's IP address is the destination. And remember, it takes that request's source MAC address as a way to populate the destination MAC address for the response. It's there in the ARP table as well now. So now, PCB can send its response. That response now arrives on the switch. The switch goes, ooh, I just received something on interface 02. Let me check. Do I know that source MAC address? 01, 02, 03, 04, 05, BB. No, I don't know it. So the switch goes and puts that in the MAC address table associated with interface 02. Then the switch goes and checks destination MAC address of this frame, 01, 02, 03, 04, 05, AA. And it says, yeah, I've got a record there, and if I send it out of interface 01, it should get to the recipient. So let me do that, says the switch, and out it goes. Now, PCA receives that ARP response and goes, ooh, that person I was looking for has replied. Now I can see what their MAC address is. And PCA can now put that record in its MAC address table. Now that the original PC has learnt the MAC address of 192.168.02, it says, okay, now I can get that ping packet back, and this time I can now put the destination MAC address in the DMAC field, 01, 02, 03, 04, 05, BB. And this PC can at long last send the ping. The ping arrives on the switch on interface 01. Obviously the switch doesn't know it's a ping, it doesn't care, it just sees MAC addresses. And it says, ooh, I've seen this MAC address before, so I don't have to worry about it. And it's going to this MAC address, and I've got that MAC address there. So let me send it out of that interface. So it's going to go out there now to PCB. And by the way, this example didn't just teach you how the switch works and how the traffic's going to end up going around, although it did actually. But I also taught you how the address resolution protocol works. This runs always when you don't know the recipient's MAC address. This is how we can find out what the MAC address is despite it not being predictable. We ask. And the way we ask is by yelling out to everybody in the LAN, hey, who is responsible for this IP address? I want to know what your MAC address is. That is basically what ARP does. It goes and finds out what the unknown MAC address is with a known IP address. Now in this case, we knew what the IP address was because of the ping packet. In other situations, we might have used a host name or something like that, and some name resolution service like DNS would have given us the IP address, and then ARP takes over once we've got the known IP address. So now let's move on and look at a couple different types of switches you can get. The first major category you want to be aware of are managed and unmanaged switches. Now the key thing about a managed switch is this is the kind of switch that you can log into and configure things on it. Whereas an unmanaged switch, it's a simple switch. You plug it in, you cable it up, and it does its thing. Both switches will ultimately do the same stuff we've just looked at. But a managed switch gives you access to a bunch of cool configurations and settings that we're going to look at with some later videos on more advanced switch features. So how do you tell them apart? Well, on the left there, you've got a managed switch, and on the right there, you've got an unmanaged switch. And the way I know that the one on the left is a managed switch is that little interface there I've circled in red. Now, I tried zooming in on this picture, and sadly you can't see the writing, so you have to take my word on it. But that interface that's circled in red is labeled console. As soon as you see an interface labeled console or con0, that implies that is the interface that you plug into to apply configuration. You'll use one of those RS232 to RJ45 console cables, or one of those rollover cables we spoke about in the cabling and connectors video to apply your config. Now don't worry, if you've got an unmanaged switch, it's just as good as a managed switch. The only difference is you can't choose any settings. But if you've deployed a managed switch and never ever applied a setting to it, it's fine. You cable it up, it does the basic switching like an unmanaged switch does. You don't have to go and turn anything on. But believe you me, in an enterprise environment, the settings and features that a managed switch brings to the table are well worth it. Then we get desktop or small office home office switches versus enterprise switches. Now, desktop switches are usually quite small, compact, run from one of those little DC power bricks or wall warts, as some people call them, and usually have a couple interfaces, very rarely more than 8 or 10 interfaces. They're often also going to be a nice shape that's easy to have in the home environment. It's not bulky, it's not heavy, it's easy to put out the way. I've actually got one screwed to the back of my desk as part of cable management, just so that I can connect a bunch of things that I've got sitting near me right now. Then you get enterprise switches. Bit bulkier, normally loads more interfaces, but the key thing about enterprise switches is they come in rack unit form factors. Usually most switches like this one in the picture here are 1 rack unit high, and you can put them in a network cabinet, server rack, whatever, because again that one in the picture there is probably the 19 inches wide it needs to be to fit in a networking cabinet. You sometimes do get slightly smaller enterprise switches that aren't 19 inches wide, but they will normally come with very long armed brackets so you can mount them in a network cabinet or server rack. Now yes, I did reuse the managed switch picture, but an unmanaged switch can also be in an enterprise form factor too. Then the next type you get are fixed and chassis switches. Fixed switches, like the unmanaged switch or the managed switch that we looked at previously, have a fixed number of interfaces. You can't change them. It is what it is. You get what you get. If you wanted more interfaces, you should have bought the one with more interfaces. If you've got too many interfaces, you should have bought the one with fewer interfaces. You know, it's a bit brutal, right? But then you get that very elegant, cool looking chassis switch over there. What's going on there? Well, that still mounts in network cabinets, assuming you can find one big enough for that bad boy, and obviously server racks. And what happens is, all of those interfaces there are removable cards. You can take it out and put maybe a better processing unit in, or another fabric unit. It allows you to decide how many interfaces, what kinds of interfaces, and how much processing power the switch is going to have. Now, this is not your average kind of user LAN switch. This is the kind of thing you'll find in data centers and cloud provider environments and ISP networks and stuff like that. These are pretty badass switches. They're really cool. And they also have redundant power supplies as well, because I mean, when you got this level of coolness, you don't want something as simple as a faulty power supply taking it down. And they are very expensive. I'll let you go do some homework on how much they cost. Just make sure you're sitting down when you check what the price is. And then you're going to come across this thing called a stackable switch. And that's what it looks like. Huh? That just looks like a bunch of switches cabled together. Normally. Why is it stackable? Well, switch stacking is going to use a special kind of cable. And what it does is it allows you to get multiple switches, usually manageable, to work together as though they were a single logical switch. It's a pretty cool technique, but in my opinion, you don't need to know much more other than that's what it is. for Network Plus, because you are going to want to try and stick to the same vendor, preferably the same model of switch if you're going to do stacking. And the reason why you want to do this is so that you can expand on connectivity and processing capability without having to go through the expense and challenges of getting a chassis switch. Because in some cases, even the smallest chassis switch is overkill for what you need. Now, knowing me, I'm going to find a way to tell you more about stackable switches later on, because I really dig networking and I want you guys to be kick-ass at it. But before we do that, we need to draw a line for this video. And as far as I'm concerned, that's enough for the basics of switching for now. But don't you worry, we're going to come back to switches more often with some of the more advanced features. We'll talk about things like VLANs, spanning tree protocol, and some other cool things. But for now, I want to say thank you for watching. If you enjoyed this, and you got anybody you know that wants to also learn Network Plus, don't be afraid to share this video with them. Otherwise though, I'll catch you in the next video.